dx square minus y square and dz square. That's why we should write 5 boxes for d orbital. 1, 2, 3, 4 and 5. F orbital has 7 orbital. F subcell has 7 orbital, and for that we should write 7 boxes. Whenever we are going to draw orbital of F subcell, so we have to draw 7 boxes. 1, 2, 3, 4, 5, 6 and 7. 1, 2, 3, 4, 5, 6 and 7. So we must memorize these 4 subcells and their number of orbitals. Now, next point, we should memorize the maximum number of electrons that can be filled in a subcell. Number 2, maximum number of electrons that can be filled in a subcell. S subcell has only one orbital, so maximum number, here I am writing subcell, maximum electron. So S subcell, maximum number of electrons that can be placed in S subcell will be 2. In P subcell, we can add maximum up to 6 electrons. Less than 6 can be added, not more than 6. P subcell will get the electron. D subcell can get maximum electron of 10. Similarly, F subcell can be filled with 14 electron. In another way, we can also understand, since S subcell has one orbital, that means one box, and each orbital can get maximum of 2 electrons. So S subcell can only add 2 electrons. P subcell has 3 orbitals. Each orbital has the capacity of maximum 2 electrons. So there will be 6 electron maximum in P subcell. There are 5 orbitals in D subcell, and each orbital can have maximum of 2 electrons. Therefore, D subcell can have maximum of 10 electrons. Similarly, you should understand that since F subcell has 7 orbital, maximum electron in each orbital can be placed 2. There can be maximum capacity of F subcell, that will be 14. A 1, 2, 3, 4, 5, 6 and 7. That is 14. So we should memorize S subcell can have maximum of 2 electron, P subcell 6 electron, D subcell 10 electron, F subcell 14 electron. These two we should memorize. Then third point is, what is the energy order of subcells in an atom of an element? Energy order, that is third point. It is decided by Aufbau principle. Aufbau principle. What is Aufbau principle? It gives us the order of energy of subcells in an atom. In different way, I am explaining the energy order. First, we should understand in first orbit there can only be one subcell. In second orbit there are two subcells, 2s and 2p. In third orbit there are three subcells, 3s, 3p and 3d. In fourth subcell there are in fourth orbit there are four subcell, 4s, 4p, 4d and 4f. And in the same way we can go 5s, 5p, 5d, 5f, etc., 6s and etc. When we are understanding this, that first orbit has one subcell, that is 1s. Second second cell or orbit has two subcell, 2s, 2p. And then third orbit of an atom has three subcells, 3s, 3p, 3d. Fourth orbit have four subcells, 4s, 4p, 4d, 4f and so on. Crossing, by making a cross line, we can understand the order of energy. Just first electron first enter into 1s, that means 1s has the lowest energy. After that 2s has lowest energy, then 2p and 3d, 2p and 3s, then 3p, 4s, then 3d, 4p and 5s, then 4d, 5p, 6s, etc. So you must write in this way the order of energy. The same order we can also write in this way. Suppose electrons, just like water, whenever water comes from a tap, it comes from upper side. Suppose here is a valve just, and electrons are coming from this side, but it always goes first into lowest energy level. When lowest energy level is filled, then it comes to the upper energy level. When second upper is filled, then it comes to next higher level. So energy order is 1s, 2s, 2p, 3s, 3p, then 4s, then 3d, then 4p and so on. The energy order is like this. Energy increases in this order. That means first electron should be added in first, it filled first, then it goes into second. When it is completely filled, then it comes into 2p, then it comes to 3s and so on. The same order you may also write as this one. 1s has lower energy, then 2s. 2s has lower energy, then 2p. It has lower energy, then 3s, then 3p, then 4s, then 3d, then 5s, and so on. You can write the energy order in many ways. Once you understood the energy order of subcells in an atom, then we should know the Pauli exclusion principle, that is fourth point. Pauli's exclusion principle. Actually, Pauli exclusion principle has a statement: no two electrons in an atom can have all four quantum numbers same. But to simplify this statement, you can only understand this one. It means in an orbital, two electrons must have opposite spins. This point helps to understand the electronic configuration box. That means orbital wise electronic configuration or box diagram electronic configuration. Let me explain electronic configuration now, and then we will come into Hund's rule. Just we are writing the electronic configuration of some of the elements. Suppose we have to write electronic configuration of carbon 6. We should write 1s, then 2s, and then 2p. Because the lowest energy subcell is 1s, then higher energy is 2s, then little more higher is 2p. And we know the capacity of electron. So 1s subcell can have 2 electrons only. And the remaining 4 electrons, how should be distributed? It comes to second 2s. Now it is 4. Then the remaining will go into 2p. So electronic configuration of carbon should be 1s2, 2s2, 2p2. Let me write the electronic configuration of nitrogen. 7 electrons are to be distributed into subcell. First you add into 1s 2 electron, remaining 5 electron. Next you go into 2s 2 electron. Now remaining electron are 3. So you should add in p. P has capacity 6 electron, but here we are, there is a mistake. Here we are placing only 3 electron. All 3 should be given into p. So the electronic configuration of nitrogen is 1s2, 2s2, 2p3. Let's take some more example. Oxygen 8. Again 8 electrons are to be distributed into subcells. 1s2, 2s2. Now the remaining electrons are 4. So 2p4. Next, fluorine 9 electron. We should write 1s2, 2s2, 2p5. So in this way, to understand the energy level of subcell, capacity of electron, how much electrons should be placed into different subcell, then we can write the electronic configuration easily. Now one more rule should be known, that is Hund's rule. Hund's rule. What is this? Hund's rule is electron field into orbital singly first with parallel spin. Electron placed field, electrons field into orbitals singly. First, with parallel spin, before pairing. In the same point, I shall say in this way, in different orbitals of a subcell, when you are placing electron, you should write one electron each to the orbitals in parallel spin. When all the orbitals get electron one each, then you should start pairing. For example, let us take example. Suppose we have to write the electronic configuration of nitrogen once again in box diagram method. So 1s, 2s, 2s and 2p. As we know, 2p subcell has 3 orbitals. These 3 orbitals can be written in various ways. According to Hund's rule, we should write the remaining 3 electrons 1, 1, 1 in parallel spin. We should not write this way, or we should not write this way, or any way. All these are wrong. All these are wrong according to Hund's rule. Let us take some other example. Take example of oxygen. Total electrons are 8. As we know, 1s2, 2s2, 2p4. So in box diagram method, 1s has one box, 2s has also one box, 2p has 3 boxes. So 2 electrons in an orbital should be written in opposite spin according to Pauli exclusion principle. So 2 electrons must be in a opposite spin. Now the problem is how to express these 4 electrons, because there are 3 orbitals and electrons are only 4. So first, according to Hund's rule, we should write 1 electron in each in parallel spin. Only then either of the 3 orbitals should be paired. This is the correct method. Take some more example. Let us take example of subset element sulfur 16. We should write subcell wise configuration 1s2, 2s2, 2p6. Now together it is 10. So remaining 6 electron 3s2. Now it is 12. So remaining 4 is in 3p. Box diagram configuration. S subcell has one box, that means one orbital. P subcell has 3 boxes, that means 3 orbital. S has one box and P has 3 boxes. Here 2 electrons of an orbital should be in opposite spin. These 2 are in opposite spin. 1, 1 and then pairing. So 2 electrons of S should be written like this. Here 1, 1, 1 and in parallel spin, then either of the orbitals should be paired. I think now every student will understand electronic configuration. Let me explain 2 more examples. Chromium 24. Electronic configuration of chromium should be written like this: 1s2, 2s2, 2p6, 3s2, 3p6, then 3d, 4s2. So 4s should be written first, then 3d. Now total electron, it is 18. It is 18. Now it is 20, and remaining 4 should be in 3D. But actually we have not made any mistake to write this electronic configuration. But it is said, yeah, it is observed that this case is not correct. It is wrong. Although by principle it is not wrong. But observation says that electronic configuration, correct electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d, and then 4s. S has only one electron, D has 5 electrons. Why? How can we explain the correct explanation of chromium should be 3d5 4s1, and why it should be D should go back side and 4s should go upper side, that means in higher energy level? These two have the explanation. First, electron has negative charge and nucleus, electron revolve around nucleus. So as soon as electron added into 3D, it comes back because it is the orbital, it is subcell or orbital of orbit number 3. 4s is orbital or subcell of higher energy level, that means fourth orbit, which have higher energy. So 4s will go upper side and 3d will come back side once electron is added. So this arrangement takes place. Now second point is, half filled electronic configuration is more stable than other electronic configuration. So 3d 5 is more stable than 3d. 3d 5, which is half filled is more stable, and 3d4 is less stable. Because half filled and full filled are more stable. Similar is case in copper also. Copper has electronic configuration 29. We should write electronic configuration like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. But it is not correct. Wrong. Correct is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. Again, same point comes. 3d comes backside when electron is added, and 4s goes upper side. And it is also the case of full filled. So 3d10 full filled electronic configuration more stable. In this way, we could understand the electronic configuration of elements. I think you could have better understanding now. Thank you.